Right, probability is another topic covered on GCSE, and this would normally be stated as a straightforward fraction. For example, you could toss a coin, heads or tails. That would be a half. You got half a chance of getting heads, half a chance of getting tails, and the full options must add up to 1. So that's okay there. You got half plus half equals 1. And if you toss a dice, this is just a poker dice, which the principle is the same thing. Each head will have the probability of 1 over 6. So you can imagine that every head is 1 over 6. So that will obviously then 6 times that will obviously add up to 1. And then you've got all kinds of probabilities with respect to a card deck. You could obviously, when I say obviously, the chances of getting a club, from just from knowledge of a deck of cards, it'll be a quarter. But say, for example, the chance of getting a queen, well, that would be 4 over 52. And as you know, you can simplify that down. That'll be 1 over 13. And so on. So the point is, you state all these probabilities as fractions. Obviously, emphasising that because you have all these people who are trying all the time to bring their calculator out and convert things to decimal numbers, but that's not going to work here. It'll work here for a half, because a half does actually equal 0.5. A half equals 0.5 is a decimal number, and that is exact. But you're not going to be able to represent a sixth or 1/3 exactly as a decimal. So, basically you just leave them as fractions. Resist the temptation to get out your calculator. Now, another topic would be correlation. You might have the results of an experiment with 2 variables. You might have sort of numbers like this. You might have numbers like this. Now, the question is, can you sort of draw a straight line through there to indicate that these results are correlated in some way? Well, here you seem to have a bit of a mess, so there doesn't seem to be any connection here. I should state that these connections will be given a figure somewhere between 0 and 1. So, there doesn't seem to be any correlation here, but I'll look at this in more detail. It may be, if I was to draw a straight line there, I could maybe draw a straight line like that. And that would sort of seem to be a good representation of those figures, approximately. I mean, I would say something like that. I don't know. Say, okay, 0.8 or 0.9. That's typically what would happen in a GCSE exam. You get a set of readings like this, and you just have to give a number between 0 and 1. So I'd say here 0.8, 0.9, maybe, any sort of... there's normally a bit of leeway. But I should stress that this is linear correlation. Okay, can you connect these two things by a straight line? Variables can be correlated by much more complicated formula rather than a straight line, or But that's at GCSE level. We're just interested in, can they be correlated linearly, i.e., by a straight line? Now, this one here, I would say that they were very highly correlated, okay, because I've given it to sort of a 0.8 or a 0.9. I should actually say in passing, actually, that you're very, very unlikely in an experiment to get them all exactly on the line, which would correspond to a correlation of 1. That would be very, very unlikely. That would indicate you've somehow fiddled the experiment. So a good correlation is likely to be something like 0.9 or 0.8. Now, if I don't know whether you can see this properly. This, hopefully hopefully you can see the flags anyway. Unfortunately, this hasn't printed out very well, but hopefully you can see the flags there. The flags are indicating particular nations, and on the horizontal axis we've got the number of Nobel Prizes per head of the population, and on the horizontal axis we've got chocolate consumption per head of population as well. And looking at this, you say, well, is there a correlation? Well, down here there seems to be quite a good correlation. It goes a bit adrift here, but at the same time there's a sort of symmetry to these ones that are these outliers here. So is there a correlation here? Well, I could say that there's a correlation. It could be something like 0.7 or 0.8. As I say, that would suffice at GCSE level just to cover, if you put down 0.7 or 0.8, either of them would probably get the mark. You don't have to be too exact. You're not expecting a too exact answer here. But that's what I would say. But it does actually have a figure up here. It claims that the correlation is 0.791. But in real life, if it's an exam question, 0.7 or 0.8 would suffice in my view. But the point is, they're now saying that there's a good correlation between the number of Nobel Prizes won by a nation, adjusted per head of the population, and its consumption of chocolate. So there is correlation there, there's a good correlation there, but is there a causation? Is there a definite connection between the two? And I think, given the nature of the two variables, I think that we could say, okay, there's a good chance that there is no connection. There is no causal effect here. There is correlation, but there is no causal effect. And you've got to be careful here. I mean, it'll be a bit like this, that okay. This is not drawn to scale, but that's everything inside this circle represents the correlation, things that are correlated. But this down here represents the ones that are actually connected, where there's a causal effect between the two. So to having a causal effect between the two, you do need correlation. But because there's correlation, you cannot say that there is causation. I mean, you probably know this already if you were to think about it. There's a TV programme on BBC Radio which I can recommend for this, more or less. It's not on every week, but when it's on, I would recommend you listen to this. And their sort of motto all the time is correlation is not the same as causation. Okay, indicating this is happening all the time. People are getting up a correlation, and then they're assuming that there's a causation between the two, and more or less quite often go around disproving this claim. As I say, you can probably think in your own life, you probably come across this quite often, and it happens quite often with respect to, say, governments, claims by people in government. They'll say, okay, this particular government has been in power for 4 or 5 years, and the crime rate's gone up, and the unemployment rate's gone up, and all this type of thing. So there is correlation there that all these things have been happening during the time that the government has been in power. But that does not say that it's causation. That does not say that the higher crime rate has been caused by the government or anything like that. I mean, that would just be rubbish. But as you know from practice, that happens all the time. If we were to take a correlation and to decide that there was actually a causation, there is a higher thing to then consider as to which way round the cause and effect is. And again, this is not really something you consider at GCSE level, but it's worth considering now we've brought the topic up. I mean, you might be able to. There are, for example, videos that you can draw up on YouTube, where you've got someone standing in front of a windmill. The windmill's going round, and this guy's claiming that there's a high wind because the windmill's going round. he's getting the cause and effect around the wrong way. Obviously, he's doing it jokingly, but you know what I mean. That's a good example of, in a joking way, of the way that people can get cause and effect around the wrong way. Well, actually, this is taking us to great extremes here. Again, you don't really need this at GCSE mathematics, but it's worth noting, as I say, there's a quote from the good soldier Schweik, and he says, "War is great. It is always the other person's fault." And to me, this is just an extreme example of confusion over cause and effect. I've got a quote here from Hannah Fry. Every single person who confuses correlation and causation ends up dying. So, I mean, there is correlation there. You've got two quantities there which are correlated. There is a correlation between those two conditions, but there is no causation. Now, another feature we need to consider is extrapolation. You might have, say, a graph, and you have a graph like that, and the question might say, can we? Well, that's a bit dubious. Can we conclude from this graph that as time goes on, it'll go on in a like manner? And the GCSE question, if you get to ask that in a GCSE question, the answer is always no. You cannot extrapolate into the unknown, if you like that. So that's all you do. You say no, you cannot extrapolate, and then you get the mark. I mean, in real life, it depends what we're dealing with. You know, if you're dealing with a business which is confident that sales will grow and they've got good reasons for doing this, they might expect that it will actually go up in like manner, but they can never be 100% certain. I mean, there are obviously examples to counteract this. I mean, people are always claiming that life expectancy is going up. So, say that's life expectancy up to now. Can we assume that it's going to go up into the like manner, and then, therefore, can we forecast in what year people are going to be living till 400 years old or something like that? A similar example I can think of is that at one stage the world record for the 100 meters was reducing in a way that could be linearly correlated. So again, it's the same thing. Can we extrapolate from that and work out sometime in the future when people will be running 100 meters in 2 seconds or something like that? I mean, it just can't be done. We just cannot extrapolate automatically from a graph. Not 100% anyway. And sometimes it's considerably less than 100%. Sometimes it's 0. So again, we can go on forever on this topic. I mean, but this is just supposed to be a brief overview of the GCSE syllabus, so I don't want to go on forever. I could probably just make one extra point. Say for example, you're talking about a constant crime rate. You know, you live in a place where you've got a constant crime rate. Well, the crime rate is very, very unlikely to go like that. It's probably more likely to go, you know, something like this. That would be classed as a constant crime rate because it's got an average. It's got a sort of definite average, which. Well, you know what I mean. This straight line could be taken as the average of this crime rate. So in one sense, it is constant. Now, the thing is that can we extrapolate? Can we go there, get all the information from there, and extrapolate what the crime rate is going to be in the future? Well, no, we can't. You know, it would be too complicated. Someone else might come along and say, okay, at this point, and say, okay, the crime rate has gone up. I'm going to introduce measures at this particular point. And when they introduce special measures, whatever it is, you know, increased punishment or whatever it is, then the crime rate goes down, and then they claim that there's a causation there. There's obviously a correlation. They've introduced measures, and the crime rate has gone down. So there is a correlation there. But is there a causation? Well, by virtue of this being a thought experiment, on this particular thought experiment, we can see that actually there is no causation whatsoever. So I'm just ramming the point home. Sometimes on a particular road, you can get roads turning into a traffic black spot just by the way random numbers work. You get a particular large number of comparatively large number of accidents on a particular stretch of road, not because of anything other than that's just the way random numbers work. If you just do nothing about it, then if you do nothing about it, then the traffic black spot will just go away automatically. But you can imagine that someone say, okay, there's a black spot here, we'll introduce calming measures or something like that. The traffic accidents will cease, therefore they claiming that there is an actual causal effect there. But, again, in that scenario that I've just imagined, but there would be no causal effect. There is a correlation, but there is no causal effect. And although I've made it up, that would be a situation which does actually occur quite often on the roads. So really, that's probably all I need to say about this topic in brief. In the old days, there was a coursework on the GCSE, which actually allowed people to go into the topic a bit deeper. They would have various topics. One topic would involve comparing groups. I normally used to say, okay, for clarity, you could compare male and female, get a male group and a female group and compare them. Now, the thing is, if you compare groups, you will always get a difference. But the point is that if you compare identical groups, you will always get a difference as well. If you compare identical conveyor belts in a factory, then you will always detect a difference. It could well be that if you observe it over 10 minutes, conveyor belt A will be better, and if you observe it over 20 minutes, conveyor belt B will be better. But the idea is that overall, or averaged out, they will be identical, but when you actually observe them, they will be different. It could be various reasons. If they're stacking biscuits into, say, 300-gram packs, it is impossible to get a whole number of biscuits into a pack that measures 300 grams absolutely exactly. So you can see that there's a scope there for differences. Differences if you measure them over comparatively short distance, over comparatively short periods of time. There's some analogy of that actually. What do we take of the differences? Well, there's an analogy if you're to toss a coin, going back to the coin again. This is not measuring two groups, but if I was to toss a coin 1,000 times, then the ideal situation would be 500 times 500. That would be the expectation value, i.e. that's the ideal value. If I was actually to do it in practice, I would be very, very unlikely to get 500 of one and 500 of the other. I might get 490 and 510. And the questions would then be, this is different, but is it still compatible with the idea that this coin is a fair coin? And in general, most people would probably say, okay, it is compatible, although it's not 500. And you can see that as a percentage, really, taking into account the size of the sample and so on. If it was, say, a sample of 30 and you got 25, okay, the expectation value there would be 15. So you've only got a variation, again, of 10 lower and 10 higher. But in that particular case, you would expect it to be a bit more suspicious. Again, it's not a particularly high sample, but probably take if I came across something like that, I'd probably do a bit more, do a few more coin tosses and increase this size of the sample just to be sure. But it's not particularly. You'd have suspicions on something like that. But if it was say 10, say you got 3 and 7. Say you tossed it 10 times, you got 3 heads and 7 tails. You wouldn't be particularly suspicious there, because you might be aware that if you were to increase the number of tosses, it would even itself out a bit more, become a bit more 50-50. So there you got the idea that small samples you've got to be very suspicious of. In order to be a sample to be representative of the population as a whole, it helps if the population is quite large. And typically you would going back to the coins again, if you had to try and test this, the formal way would be you would set up a null hypothesis, which is a sort of nice neutral hypothesis, saying, okay, this coin is quite fair, okay, and you get this figure and say, okay, is that enough to reject the null hypothesis and go with the alternative hypothesis? And okay, we decided probably that's best to just go a figure like this, so best just to go with the null hypothesis. But it depends how far out can you go. If you get 470, 530, what do we do then? At what point do you reject the null hypothesis and go with the alternative hypothesis? There's a level of uncertainty here all the time. Unfortunately, when I say unfortunately, GCSE level, they never actually sort of give you the actual tools to actually put any figures on this. So it's really a case of, okay, if you're presented with this, you say, okay, that's not too far from a 50-50, so I'll go with the null hypothesis or something. It's all very hand-waving. At a high level, you would actually put some figures on it. And quite typically, they would say, okay, 95%, say maybe. The important word to look at a high level is significance. Okay. If they say in an article that a statistic is significant, then that means that the statistic is of some real value. It's not the way that you might go down the pub and some people are throwing statistics around to try and prove something. Where quite often these statistics don't actually are quite worthless, or they don't show what the is purported to be being shown. But if the statistic is significant, then that is a high level statistics. And they quite commonly say, okay, it's significant at the 95% level. That's quite common. And what that means is if you were to do the same test many, many times, then on average, 19 times out of 20 you would be right, and once out of 20 you'll be wrong. And, that's just the way things are. Statistics does not actually prove anything 100%. There is a certain level of uncertainty. I mean, okay, this might be, I might have possibly said too much on this topic already, given that it's not really part of the GCSE syllabus, but it is useful in everyday life. I mean, this situation is not too dissimilar from in a law court, where the null hypothesis would be that someone is innocent until proved guilty. So that's a nice neutral null hypothesis. And then, okay, one side tries and proves them guilty. If they haven't got enough evidence to reject the null hypothesis, then they just go with that and say, okay, this person is not guilty. And in that sense, not guilty is not exactly the same as being innocent, despite what people claim. You could increase the number of innocent people in the not guilty group, if you like, by adopting a different null hypothesis. You could say, okay, this person is guilty until proved innocent. So all other things being equal, that would mean that in the not guilty group, the percentage of people who are actually innocent goes up. But at the same time, it means that in the people who've been proved guilty, the number of innocent people goes up as well. So it's a playoff. But at the same time, there's a certain sort of not necessarily mathematical point to this in actually drawing up the null hypothesis in the first place. The null hypothesis of being not guilty until proved innocent is a sort of a nice neutral hypothesis to make. I'm not too sure that when I said before that people could compare male and female groups, the nice null hypothesis there is to say, okay, there is no difference between the male groups and the female groups, and they would reject that only when there's strong evidence to the contrary. Right, so that's really all. There's a couple of things I should have said right at the beginning, actually, just to emphasise this, is that statistics don't actually really prove anything. They just suggest something. So the best thing to say is statistics suggest something or other. As I say, that normally they do actually put a level of significance on it as well. 95% is probably the lowest. It could actually say, okay, 99%, but that would involve a lot more work possibly, or the figures that you have don't actually give you enough ability to state something at 99%. But I mean, 95% is probably the lowest you'll come across. And at the same time, that's if people can live with a law court. I mean, if you go before a law court, no one is ever saying that the verdict from a law court decision is 100% true. Okay, they accept that there's a certain amount of errors going to creep in. So if they can accept that this deeming of people to be guilty or not guilty does carry a certain amount of uncertainty, it's not going to be absolutely 100% foolproof, then they might be able to thereby live with this idea that things are stated to a significance level of 95%. The idea that statistics might suggest something with a significance level of 95%, that might be something that they can live with, if they're happy with the way that law courts live with a certain similar uncertainty as well. Yeah. I should also state that one of the founders of statistics, Jack Bernoulli, he said that statistics was something that counteracted our intuition. So that doesn't really occur all the time, but it's something to be basically bear in mind. So many people think that things are so obvious, but the mathematics, when you look at the mathematics, it is not so quite often. Yeah. So basically, what I've said there about the correlation and the extrapolation is probably sufficient enough actually for what you might meet in a GCSE examination. But the probability, I'm going to have to spend a couple of possibly dedicate a couple of more videos to the idea of probability. Anyway, cheers for now.